Sure.
Okay, so hi everyone. It's a pleasure to have Dr. Jens Kammerer for our Astro seminar today. And first, thanks Jens for accepting our invitation despite the late time in Baltimore. So Jens was educated at ETH Zurich and then came to Australia to carry out his PhD at ANU under the primary supervision of Mike Ireland. So Jens spent also a significant amount of time at Garching during his PhD and has now just completed his PhD in March of this year. So Jens just started working as a postdoc now at the Space Telescope Science Institute in Baltimore. And there Jens is working on high contrast imaging of exoplanets with JWST on the one hand, and on exoplanet yield estimates for future direct imaging missions on the other hand. But today he will tell us about one exciting science topic done with a relatively new instrument at the VRT, that is the gravity instrument. So take it away, Jens.
Yes, thank you very much, Valentin. And hello, everyone. Hello from the US. It's really great to be with you at Monash today. As Valentin already said, I spent about 2 years of my life in Australia when I did my PhD at ANU in Canberra. In the middle of my PhD, I decided to go to ESO for a year for a studentship. And then I never managed to return back because of the pandemic. So I missed my friends and colleagues in Australia quite a bit over the last years. And it's nice to finally be back, although of course, only virtually. Now today I'll be talking about high contrast imaging with young giant exoplanets with the gravity interferometer. And it's in fact only since very recently that we can observe exoplanets with optical long baseline interferometry. So that's all a very recent field. Now we should be showing results from the last 3 years or so. But before we get started, I would like to give some credit to my amazing collaborators, which have all played key roles in the work that I will be showing today. And also I would like to thank Valentin and Rio for reaching out to me about this colloquium, of course. Can you see the slide moving? Yeah, it should work. Okay. Yeah, so what's on the menu for today? I want to start by illustrating a bit how we do actually observe exoplanets with the gravity instrument, just to make sure that we're all on the same page and that you know what we are actually doing. Then I want to talk a bit about the correlated errors that we find to be present in the gravity data and how we try to mitigate their impact on the final detection limits. So that's what I've been working on mostly during my ESO studentship in Garching. And then I want to show some of the exoplanet science highlights that we've been achieving with gravity over the last 3 years or so. And finally, I'd like to talk in a bit more detail about the HD 206893 system, which is an exciting debris disk system that has 2 inner companions. One of them is also directly imaged and is also the reddest known substellar companion. So I've been working on this system for the last year or so. And in the end, I'll give a brief outlook into the very near future of optical long baseline interferometry. Okay, so what is gravity? Gravity is an instrument at ESO's Paranal Observatory in the north of Chile near Antofagasta. Many of you might have probably been there before. You can see here the 4 8-meter unit telescopes and here the smaller 4 1.8-meter telescopes, auxiliary telescopes. And here the telescope control room. And there in the middle of the mountain is the VLT lab, the VLT interferometer lab. And of course, gravity being an interferometric instrument is sitting there in this VLT lab and combines the light from either the 4 unit telescopes or the 4 auxiliary telescopes at the same time. Now with the UTs, you can obviously achieve better sensitivity because they have much larger collecting area, but with the ATs, you get access to a larger field of view and also not as oversubscribed as the UTs. Now gravity being a phase reference interferometer achieves co-phasing of the light from the different telescopes with this system of delay lines, which are located in the basement of the Paranal mountain, where you would find these mirrors that are mounted on sledges, which move back and forth on these rails to basically equalize the optical path between the astronomical source and the gravity instrument through all of the 4 different telescopes. So that's pretty much like the adaptive optics system of the interferometer. And finally here, you can see the gravity instrument with the QR open so you can see inside. And the exciting thing about gravity for our exoplanet observations is that it has not only one, it has 2 interferometers. It has a fringe tracker and a science spectrograph. And the Fringe tracker operates at a very high temporal resolution to adapt the length of these delay lines in real time to the atmospheric turbulence. And the science spectrograph operates at a much higher spectral resolution to get some high resolution spectra of the science targets. Now, gravity was designed to observe the galactic center and to measure to a very high precision the orbits of the stars around the galactic center. And in order to do that, the interferometers of gravity, the Fringe tracker and the science spectrograph were equipped with optical fibers, which you could then put onto a specific source in the field of view. And for example, you can put the science spectrograph here on the galactic center itself and the Fringe tracker on a bright reference source. In this case, it's IRS-16. And then by measuring the optical path difference between those two interference fringes, you can basically measure the differential astrometry between the two sources. Of course, projected onto the telescope baseline. And since the VLT has these large, or the VLTI has these large baselines of up to about 130 meters, you can achieve very high astrometric precision with this technique. Now, something that you should keep in mind for later is that, of course, there's an instrumental OPD associated with both the Fringe tracker and the science spectrograph, which you have to calibrate. And for that, you would basically swap with the science spectrograph from the galactic center to the reference source and back every now and then. So that's done with a 50-50 beam splitter. And then you can observe sometimes the reference source simultaneously with both the Fringe tracker and the science spectrograph. And by this, you can then measure this instrumental OPD and calibrate for it. Now, in the case of exoplanetary observations, we find ourselves in a very similar setup. There's also a bright reference source, which is the host star. In this case, it's HR8799, for example, which is observed with the Fringe tracker. And then you have an exoplanet, the science target, that is observed with the science spectrograph. In this case, it's HR8799E at about 400 milliarc second separation. And here, these observations are also done in on-axis mode, which just means that we use the 50-50 beam splitter to split the field of view. For this, also the separation between the two must be less than 800 milliarc seconds, so you cannot observe all exoplanets with this technique. But of course, the disadvantage here is that you lose about 50% of the light from the planet because you use this beam splitter. So there's another mode, which is called off-axis observations, where instead of the beam splitter, you use a gold-coated roof mirror, a wedge mirror, which is actually separating the field of view into two separate parts with about 100% transmission each, so that you don't lose all the photons of the planet or half of them. But for this, you need a minimum separation between the host star and the exoplanet of about 270 milliarc seconds, so that you can actually put the wedge, the edge of this roof mirror between the two. Now, the problem with off-axis mode is that the calibration becomes a lot more difficult because now you have these two separate fields and you cannot anymore just swap back and forth with the science spectrograph from the exoplanets to the host star and back. Instead, to do the calibration of the OPD, you have to observe a well-known reference source, a binary target, with the same off-axis observing mode. And firstly, of course, such a well-known binary is not always available nearby in the sky. And also it takes about 30 minutes extra to slew the telescopes and do these extra observations. So most of the science that we've been doing so far has been done with the much easier on-axis mode. And we're actually still struggling a bit with the calibration of this off-axis data. So how does gravity see an exoplanet? This is the field of view of one of these optical fibers. And we're here observing the exoplanet Beta Pictoris C. I will talk about it in more detail later. But yeah, just to illustrate the PSF of gravity, basically, and you can see the planet as the bright peak in the center. And you get this periodic pattern here because of the sparse sampling of the apertures in the VLTI array. You just have 4 telescopes sampled over large baselines. So you get this sparse UV coverage and this periodic PSF. The field of view is about 50 milliarc seconds of one of those fibers, so it's pretty small. And also the throughput decreases significantly towards the edge of the optical fibers. So if you want to observe an exoplanet with gravity, you have to know very well where the planet is located in order to observe it to about 20, 30 milliarc seconds precision. So that's the reason why usually with gravity, we are only following up already known exoplanets. And you also see, of course, that because of this PSF, you get correlated measurement of astrometry. You get some correlation between right ascension and declination. And we have to take this into account in an orbit fitting to make use of the high precision, the high astrometric precision of gravity. Now, for an instrument like gravity, there's also many other possible sources of correlations. For example, on the instrumental side, that the closure phases, which is one of the two observables of gravity, are not linearly independent. And I will talk about this in one of the next slides in more detail. But also there could be instrumental vibrations or imperfect coupling of the light into the optical fibers. On the astrophysical side, there might be uncertainties on the observed calibrator, which can then propagate through to a systematic uncertainty on the science target, and also an effect that we call differential atmospheric piston. And I will also talk about that in one of the next slides in more detail. So during my ESO studentship, I was trying to understand what kind of correlations are present in the gravity data and how can we mitigate their impact on the detection limits. And as I said, there's two interferometers for gravity. There's the Fringe tracker and the science spectrograph. And because the Fringe tracker operates at a much higher temporal resolution, we have about 40 to 50,000 frames of data for a usual gravity data set. And from that many data, we can simply compute the correlations empirically. So I started by looking at the Fringe tracker data because that's easier. And then I just computed the correlations from some intermediate pipeline products of gravity with this empirical covariance matrix, which you can transform to correlation metrics and by normalizing with the standard deviation of the observables. So this is the correlation matrix that you get for the Fringe tracker for the visibility amplitudes, which is the other of the observables of gravity. And it's good for measuring the angular extent of the source. For example, if you want to measure stellar diameters, you would look at visibility amplitudes. And those visibility amplitudes are always obtained by combining the light from 2 of the 4 telescopes. So here's a top-down view of Paranal with the 4 UTs. And with the 4 UTs, you have 6 different ways to combine the light from 2 of them, and we call those the 6 different baselines of the VLTI, which is why you have these 6 boxes here in the correlation matrix, 1 box for each of the baselines. And then within each of the baselines, you have 5 spectral channels because the gravity Fringe tracker has 5 spectral channels. Now, by definition, the diagonal of this matrix is 1 because every quantity is 100% correlated with itself. But in an ideal world where we wouldn't have any correlations, everything else except for the diagonal here should be 0 and should be white, which you can see that it's clearly not the case. We have some very significant positive correlations. For example, here where you can see the correlations between the 5th and the 1st baseline. And now if you look at the top-down view of Paranal, you can see that the 5th and the 1st baseline, they actually share a telescope. They both use UT1. So we think that these correlations here are caused by differential atmospheric piston, which basically means that if a more opaque patch of atmosphere travels into the beam of UT1, then of course baselines 1 and 5 would be equally affected by this because they both use the data from UT1, which would give you these positive correlations. And this would also naturally explain why there's pretty much no correlations at all between, for example, the 6 and the 1st baseline, because they do not share any telescope, as you can see, and also why the correlations are about twice as strong within a given baseline, because there you share not only one, but both of the telescopes. So for the closure phases, the other of the observables, which is good for measuring asymmetrics, some asymmetries in the source. For example, if you want to find a faint companion, you would use closure phases. Those are always obtained by combining the light from 3 of the telescopes. And with 4 telescopes, you can form 4 different triangles between the telescopes. So you have these 4 boxes here, 1 for each triangle, and again 5 pixels for the 5 spectral channels of the Fringe tracker. And here you see also strong correlations of about plus or minus 1/3 on the side diagonals here, which are caused by the fact that the closure phases are not linearly independent. Because if you pick any random set of two triangles, you will find that they always have exactly one of their three sides in common. They share one of their three baselines. And this is the reason why you get correlations of a strength of either plus or minus 1/3 between those different triangles. And then, of course, the sign just comes from whether you share the baseline in parallel or anti-parallel direction. So we think that we have quite a good understanding, at least to first order, of the correlations in the fringe tracker data and also on their origin. So I tried to do the same exercise for the sign spectrograph, but of course, in that case, it's much more difficult because instead of 40 or 50,000, we only have about 30 measurements available for a usual gravity data set. But you can see that to first order, the correlation structure is relatively similar. So there's also lots of correlation here within a given baseline, and then weaker correlations between the baselines that share telescopes, and even weaker until pretty much no correlation for the baselines that do not share any telescope. And also in the closure phases, you can see these side diagonals with plus or minus 1/3. However, because they are only computed from 30 measurements, and of course with the science spectrograph, we don't only have 5, we have in this case more than 200 spectral channels per baseline or triangle. Those matrices don't have full rank and therefore they cannot be inverted. So it's pretty useless for any kind of model fitting where you would need to invert the covariance metrics to make use of the correlation structure. In order to overcome this problem, we developed an analytical model for the correlations. So you can see the models here on the right-hand side and the data on the left-hand side. And this is a very simple model with just one free parameter, which you can fit to the correlations that we observe in the data. And of course, this analytical model can then easily be inverted and can be also used for the model fitting procedures. So in order to understand the impact of these correlations on the gravity detection limits, we performed so-called companion injection and recovery tests. So we injected a faint companion into a gravity data set and tried to find it again. First with the classical approach where you would just take into account the standard deviations of the data. And then with this approach that takes into account the full covariance metrics that we have been seeing on the previous slide in from our model. And this figure here shows then the number of the correctly recovered companions as a function of the companion contrast. So if we inject very bright companions, of course, we always find them. And if we inject very faint companions, we never find them. And somewhere in between here is where we approach the detection limits of the gravity dataset. And as you can see, if you do account for the full covariance metrics, then this curve shifts significantly towards fainter contrasts, and the detection limits improve by a factor of about 2 to 3. Now, not only that, we could also show that the detections that you get become a lot more robust if you take into account the full covariance metrics. And for that, we computed the so-called confusion metrics, where you can see the number of true positive and false positive, and also false negative and true negative detections, assuming a 3 sigma detection threshold in this case. Now, in the classical approach, where you just have the standard deviations of the data, we actually found a very, very high number of false positive detections, which I find very worrying because in a real experiment, you would never be able to tell whether those detections are actually real companions or not, right? But then if we do the same experiment with the full covariance metrics, we see that this number drops very significantly and is now much more in agreement with a statistical 3 sigma result. So in summary, our covariance model doesn't only help you to improve the detection limits, but what I find probably even more important is it also helps you to have more robust detections and be able to make a statistically more robust claim about your detections. Okay, enough about correlations now. Let's look a bit about the science that we've been doing with gravity and exoplanets over the last 3 years or so. And for that, I'd like to start with Beta Pictoris b, which is one of the most famous directly imaged gas giant planets. You can see it moving around its host star in this little video here from Jason Wong in almost an edge-on orbit. Our system is about 20 million years young and about 20 parsecs away from Earth. Of course, it has been observed with many different instruments before. So here you can see in orange the GPI K-band spectrum from Chilcot et al. That was taken in about 3 hours of integration time, I think, with GPI. And in gray, you can see our gravity K-band spectrum, also in about 3 hours of integration time. You can see that we firstly achieve a little bit higher spectral resolution, but also we achieve much better signal to noise per spectral channel. And of course, this comes on the one hand from the fact that we combine the light from 4, not only one 8-meter class telescope. And also we have the much larger baselines, which help us to disentangle the exoplanet light from the residual stellar light. So the resolution of gravity, you start to see something interesting here around 2.3 microns, which is where you can start to see some carbon monoxide absorption features, some CO bandheads in the atmosphere of this giant exoplanet. So with atmospheric model fitting and free retrievals, we were able to precisely determine the atmospheric parameters of this planet. And here I basically want to focus a bit more on the C/O ratio, which we could measure to a meaningful precision for the first time for such a directly imaged exoplanet. And in this case here, we found a C/O ratio of about 0.44. Now, the C/O ratio of the Sun, for reference, is about 0.55, so a bit higher. And if we assume that also the host star Beta Pictoris has a C/O ratio of about 0.55, then somehow the exoplanet Beta Pictoris b must either have been enriched in oxygen or depleted in carbon to lower the C/O ratio during its formation. So from this C/O ratio here, we can learn something about the formation history of the planet. And just very briefly, there is 2 major theories about planet formation. One is the gravitational instability or disk instability theory, and the other one is core accretion theory. In the gravitational instability theory, it is believed that planets form from local overdensities in the circumplanetary disk, which would just collapse relatively quickly within only a few 10 to 100,000 of years into gas giant planets. So these planets here are rather hot after the formation. We call it also hot start, and they have a little bit of a higher specific entropy after formation. In the core accretion scenario, the planets would form first by coagulation of small millimeter-sized dust particles to centimeter-sized ices, and then those would grow into small meter or kilometer-sized planetesimals, and later into planetary cores, and finally into a gas giant planet over a much longer time of about millions of years. And also after formation, those objects tend to be a little bit colder and have a little bit smaller specific entropies. Now, in a paper from 2011, Karin Öberg et al. Have shown that the C/O ratio in the protoplanetary disk is varying as a function of the distance from the host star, because as a function from the distance of the host star, also the temperature varies. So as different species condense out from the gaseous to the dusty phase, also the C/O ratio of the gas or the dust is varying. And based on this paper, Matthias Nowak and the Gravity Collaboration developed a framework to trace the evolution of the C/O ratio of Beta Pictoris b as a function of the accreted solid material for this core accretion scenario of planet formation. And they found that for a formation somewhere between the carbon dioxide and the water ice lines, so somewhere here, accreted material mass of about 100 Earth masses, which sounds reasonable for a planet of several Jupiter masses, would be sufficient to lower the C/O ratio to the observed value. So that we basically concluded that this planet must have formed through core accretion somewhere between the water and carbon dioxide ice lines. Now, gravitational instability could be ruled out in that case, because for such a massive planet like Beta Pictoris b, this process would happen relatively quick, and there wouldn't be enough time to accrete enough solids to lower the C/O ratio significantly from that of the pre-stellar nebula. So one would expect the planet and the host star would have a similar C/O ratio, which is clearly not the case. Okay, in the same system, Anne-Marie Lagrange and her collaborators announced evidence for another planetary mass companion, closer into the host star at only about 140 milliarc seconds separation, so that this planet, or well, they did this based on radial velocity data, and the planet would usually be hidden behind the coronagraph for the other observations of the system that were done before. But with gravity and with the increased resolution, we were able to directly detect Beta Pictoris C. You have seen this in the previous PSF that I've been showing in the field of view of the optical fibers. We had Beta Pictoris C in the center. And it's of course very exciting because it's the first time that we could directly follow up a planet that was predicted to exist only from indirect methods, in this case from the radial velocity method. And moreover, this is also giving us more clues about the formation of these objects, because from radial velocity, we get a very precise mass estimate of the planets. And from the direct observations with gravity, we get very precise measurements of the flux and therefore also the radius of the planets. So we can put them into this plot here, Beta Pictoris B and C in the mass with this radius plot. And we can also put our predictions from different formation models into this plot. Again, here we have some predictions from a disk instability model or the hot start models in red, and then some predictions from core accretion models. And you can see it, at least for Beta Pictoris C, it seems much more in agreement with the formation by core accretion, which is also in agreement with what we've been finding for Beta Pictoris B from the C/O ratio. And that's good because, of course, we think that those planets being in the same system would have also formed through the same formation mechanism. And then we also could observe the PDS70B and C protoplanets. So this is a very exciting system also for planet formation, because it's one of the, probably the only system where we have an unambiguous detection of planets that are still in the process of formation. And you can here see this transitional disk imaged with ALMA, which has this large inner cavity where there's the PDS70B and C protoplanets which have been carving out this cavity. And with MUSE, Harvard et al. Have been finding some H-alpha emission towards those planets. So we believe that they're still actively accreting material from the circumstellar disk and are still in the process of being formed. Now, our planet formation models suggest that for such planets which are still forming, they should also form a circumplanetary accretion disk in the vicinity of the planet only. And with the high resolution of gravity, we tried to resolve the circumplanetary environment of PDS70B and C and search for such circumplanetary accretion disks. And for that, we basically looked at the visibility as a function of the baseline, and we were trying to see whether on the longer baselines we can start to resolve structure which would be which appear unresolved for the shorter baselines. And in both cases here, we didn't find any significant detection, but at least in the case of PDS70B, data was good enough to place some upper limits on the size of a circumplanetary accretion disk. And here with a model of a compact photosphere, which emits about 90% of the light, and then an extended disk, which emits about 10% of the flux, we found an upper limit for the circumplanetary accretion disk, radius of about 0.3 astronomical units. Now, the size of such a disk is governed by either the smaller of either the Hill or the Bondi radius, and from the planet formation theories, it has been predicted for PDS70B that the disk should be at most about 10% of the Hill radius in size. So, 0.1 or 0.2 or AU at most. So you see that with gravity, we are still not able to really probe the scales of the circumplanetary environments, but we're getting relatively close already. Yeah, so in the last 10-15 minutes, I would like to talk in a bit more detail about the HD26893 system, which is a debris disk system that has two inner companions. There's HD206B, which has been directly imaged with sphere, JIPA, and now also gravity, and is believed to be a brown dwarf of about 15 to 30 Jupiter masses. And there's HD206C, which is known from radial velocity and also Gaia measurements. And its mass is still highly uncertain, but maybe somewhere around 15 Jupiter masses. And then there's this outer debris disk that has been seen already before with Herschel, but has been imaged much more nicely with ALMA. that also found a gap in the disk, which could be carved by a third planetary mass companion. So with gravity, we observed HD206b, which is also the reddest known substellar companion. Here you can see a column magnitude diagram of HD206b, and you can see it's the reddest known object both in J-K and H-K colors. So there's also other known planetary mass or brown dwarf companions and some MLT dwarfs from the library in the background. But yeah, HD206b is the reddest known object in both J-K and H-K color. And if we assume that this extremely red color is caused by dust rattling with a log normal size distribution, then we find that for a visual extinction of about 2 to 3 magnitudes, this is somewhat consistent with an L3 dwarf. Now, where could the dust rattling come from? We could already rule out interstellar extinction because of spectroscopic observations of the host star, which didn't show any signs of interstellar extinction, and also reddening from the debris disk, because even if the debris disk would be viewed perfectly edge on, and we would look through the entire disk to see the planet, even in that case, it would have to be unrealistically optically thick to cause the observed reddening. So the remaining possibilities are a circumplanetary accretion disk in the vicinity of HD206b, or dust in its own upper atmosphere. Now, given the age of the system, which is predicted to be at least 50, but likely much more than 100 million years, we think that also the circumplanetary accretion disk is rather unlikely, and we have been exploring in more detail the possibility of dust in the upper atmosphere of this object. Before we look at the spectrum, let's look briefly at the astrometry, which also tells us an exciting story in this case here. So that's the orbital solutions that we got for HD206b with also previous NARCO, SCIFY, and GPI measurements. And then in red, the gravity data with a precision of about 100 microarc seconds. So that's about 10 or even up to 100 times better than some of the previous data points. Now, before we had the gravity data, the posterior distributions for the semi-major axis A and the eccentricity E showed this kind of twofold solution. There was one solution with a large eccentricity and a small semi-major axis, and one solution with a small eccentricity and a large semi-major axis. Now, once we added in the gravity data, we found that the former of the two solutions was preferred, the high eccentricity and small semi-major axis solution. Now, the interesting point is, and that's already been observed by Sebastian Marino, if you assume also coplanarity with the debris disk of the system, you would find that the other of the two solutions is preferred, the small eccentricity and large semi-major axis solution. And this could be a slight hint that the gravity data is preferring a misalignment between the orbit of HD206b and the debris disk of the system. And indeed, when we compute the mutual inclination between the disk and the planet, we would find about 20 degrees. But nevertheless, one has to treat this with some caution because the mutual inclination is a strictly positive quantity in the first place. And also the uncertainties are still quite large. So we hope that we can further narrow down this parameter space with future gravity observations. I should mention, though, that from an evolutionary perspective, it would be highly surprising to find a misalignment between HD206 and the debris disk, because we would expect that those align within only a few 10 million years due to secular interactions. So given the age of the system of probably more than 100 million years, we shouldn't find any misalignment. But maybe also this could point to a much younger age for the system, maybe around 50 or even less million years, because there's also a membership probability in the Argus moving group of, I think, about 60% is the most recent estimate. So maybe the system is much younger than people have been thinking before. Okay, so here's the gravity spectrum in red, together with some other spectra from SPHERE and GPI. And it's probably worth mentioning here briefly that it's interesting that SPHERE and GPI agree quite well in the J band, whereas there seems to be some systematic offset in the H band. So in our model fits, we have always just allowed for some relative scaling for all of the GPI spectra to make up for this systematic offset here. But yeah, we've been looking at this in more detail also with the colleagues from GPI, and we couldn't really figure out why that's the case. So based only on the sphere spectrum, Delorme et al. Have already compared the spectrum of HD206 to other known L dwarfs. So you can see in red here the spectrum of HD206b, and then in green the spectra of other L dwarfs. And yeah, they couldn't find any object that would match both the extremely red near-infrared color and also the very shallow water absorption feature here around 1.4 micrometer. Only when they added an additional layer of sub-micron sized dust particles, which would cause some additional artificial extinction to those spectra, they could find somewhat acceptable fits. And based on this experience, we decided also to add an extra layer of small dust particles to the atmospheric models in our atmospheric model fitting. So for completeness, of course, we also made fits with only the plane models, but they didn't fit the data very well. But then with the dusty models, with this extra layer of extinction, we got quite nice fits, as you can see here. So in light red, these curves here are before the extinction is applied, and then in dark red it is after the extra extinction is applied. And you can see that the fits nicely match with the observed SED of HD206b. We find a good agreement between the BT settle and the EXO-REM models, especially here about the dust grain size, which is predicted to be around 0.3 microns or so. But the drift Phoenix grid predicts a much larger dust grain size and therefore a much larger extinction over the L and M bands here, where the NACO photometry from Thomas Stolker et al. Is just not precise enough to place any meaningful constraints on these models over the L and the M bands. So we hope that with future James Webb observations of the object in the L and M band, we can get more precise measurements here and hopefully distinguish between these different models. It's also worth to highlight here that this triangular shaped H-band peak observed with GPI and also the morphology of the K-band spectrum suggests a much lower surface gravity than what has been predicted before from the sphere spectrum from Delorme. So we basically revised their mass estimate, which was previously 15 to 30 Jupiter masses, down to 5 to 30 Jupiter masses. So in principle, the object could also be in agreement with a planetary mass companion. Okay, let's also have a quick look at this inner companion here, which is known from radial velocity and Gaia observations. In fact, there's a more than 20 sigma proper motion anomaly from the most recent Gaia data release 3 and the Hipparcos data. So that basically means that the long-term proper motion of this source between Gaia and Hipparcos deviates by more than 20 sigma from the short-term proper motion that is monitored by Gaia over a few years. And this anomaly is exactly sensitive to planetary mass companions in the range where HD26893b and C, where those two planets are located, as you can see in this figure here from Pierre Cavea. So exactly there we are sensitive to planetary mass companions, which is great because we can use this anomaly then to place some mass constraints on the planets based on this Gaia data. Now, of course, we only know the orbit of B to a very high precision. The orbit of C is pretty much unconstrained. So we could only compute these mass constraints as a function of the on-sky position of that C companion, which is still unknown. And all of the parameter space here, which is white, can basically be ruled out because one of the companions would have to have a negative mass to explain the proper motion anomaly. And then if we assume that the mass of B is somewhere between 5 and 30 Jupiter masses, it would be somewhere in this region here, then we would conclude that also the mass of C could be in the planetary mass regime, or at least below about 15 Jupiter masses. So in the end, I think there's still lots of question marks in our understanding of this system. What's the mass of the inner companion? What is the nature of B? And also what is the origin of the dust and its extremely red color? Is the debris disk misaligned with respect to the inner planets? And finally, what about the outer companion? Now we try to answer these questions with future gravity observations of the inner planets and also with James Webb aperture masking interferometry of HD206b. And there's also a James Webb proposal which tries to find a companion in this debris disk gap led by Sebastian Marino. Okay, so I'm almost at the end now, and I just want to give a very brief outlook into the near future of optical long base interferometry. There's two things I want to talk about here. One is Gravity Plus, the other is SCIFY. So Gravity Plus has now been recommended by ESO for a phase A study and would bring a laser guide adaptive optics to all of the 4 UTs, and also an update to the adaptive optics system and the grism of gravity, which would enable us to observe both fainter and also closer in exoplanets, and would give us the possibility to follow up several dozens of the planets that we expect to be detected from Gaia astrometry. Then there's also Hi5, or I think it's now called SCIFY, which is a project led by Defrère, and which is an ERC-funded visitor instrument for the VLTI, which aims to do nulling interferometry. And one of the science cases for this instrument is to observe young giant planets in the nearest star-forming regions. And of course, with the current instrument, the issue here is that those regions are more than 120, 130 parsecs away, so we cannot really probe the parameter space where the giant planets are most likely. We cannot really get to this peak in the giant planet occurrence rate right now with current instruments. And with this nulling interferometer, we would be able to probe closer to this peak and significantly increase the detection probability of such giant planets, as you can see in this paper led by Alex Wallace, one of my colleagues from ANU. By about a factor of 10 or so, and even with respect to instruments like METIS at the ELT. And another nice thing that you could do with SCIFY would be to measure to a very good precision the specific entropy of young objects in the nearby moving groups. And here you could do that to a precision of better than about 0.1 Boltzmann per baryon, which would be very exciting again for planet formation theories, because as I've been saying before, the gravitational instability and core accretion predict different specific entropies for the planets after the process of formation. So we could really start to statistically sort the objects into different formation scenarios when we can observe their specific formation entropy. And with that, I'm at the end of the talk. I think you enjoyed it. I'm happy to take any questions. And while you're thinking about questions, I'm just going to show this movie in the background, which shows the light path of a light ray through the entire VLTI and the entire gravity instrument. I think it takes about 4 or 5 minutes or so. So feel free to start with questions in the meantime. And thank you very much for your attention.
Thanks a lot, Jens, for this very interesting talk. Please join me in a muted clap. Thank Jens. So please free to post your question in your chat or raise your hand. I see the.
I think I cannot see the chat. So if there's a question in the chat, could you?
It's okay. I'll read it. I see that there was an early question by Rosemary about what the acronym gravity stands for, and there was a reply, but haven't clicked on the link yet. So if you know the answer, maybe it's easier if you can answer us, Jens.
No, I actually don't know the answer.
Okay.
That's a good question. I was never asked that question, but I thought, I don't know whether it's, maybe it has an acronym, but I thought it's just gravity because they wanted to measure gravity around the black hole in the Galactic Center. But maybe that's not true. Maybe I'm wrong and it's actually an acronym.
Okay. Sorry, this is Moritz speaking via Daniel's MacBook. Jens, indeed you were right that I enjoyed your talk. I was wondering, you were showing some spectra earlier from gravity and some other instruments like GPI. I was a bit interested because it seems like the GPI spectra are smoother in a way, like they have they have quite wide arrow bands, but they seem to move very smooth. So it appears that in different frequency bands, the arrows are covariant in GPI and other instruments, but it doesn't appear to be the case in gravity. Can you explain why that is the case?
Yeah, let me maybe move back quickly to one of those slides if I can find it. Oops. Oops. Presentation ended. My computer is a bit slow.
Yeah, this one, for example.
Here. Yes, so yeah, as you said, the spectra of sphere and GPI are a little bit more smooth, and yeah, like in my opinion, the error bars that are shown here are also, at least they are tracing also some systematic errors in flux, not only the statistical errors, right? Because you can clearly see that the fluctuations of the data points are a lot smaller than the errors that are given here. So I think with these error bars, they're also trying to trace some of the systematic flux calibration errors, which we have not done with gravity. So that's one of the reasons why you see a lot more fluctuation here. Now, in the case of HD206b also, the observing conditions were not very good, which is why the signal to noise here is relatively small. In the case of Beta Pictoris, the signal to noise and the observing conditions were much better. But yeah, we have more spectral channels with gravity, which also means that we can yeah, better disentangle between the correlations among those different spectral channels with this correlation model that I've been showing before.
I actually have a follow-up question regarding this, if you don't mind. Regarding this disagreement between the GPI and sphere spectrum H band around 1.6 micrometer. So they were taken at two different epochs, right? So could there be could this be due to stellar variability? If we assume a constant stellar luminosity or stellar spectrum, what we are measuring here is the contrast with respect to the star, right? So if actually the star is a bit variable, then you might have this shift by assuming the star to be constant.
Yes, we have been comparing basically our stellar models that we use to calibrate the flux here, and we have been finding that the models itself cannot be the reason for the flux offset. But of course, as you're saying, it might be possible that the star would have some different brightness in one of the observations. But I'm not 100% sure how far apart the different GPI observations are in time, and at least, you know, in the K band and in the J band, it agrees very well, and it doesn't agree so well in the H band,
right? Yeah,
which is a little bit weird. Yeah,
I see.
So I'm not sure whether it could be associated with some stellar variability. But I guess in theory it would be a possibility.
Yeah, or it could be correlated noise. Yeah, could be stronger.
Yeah. Yes. So they also had some kind of problem like this for the Beta Pictoris spectra with GPI, and Laurent Priou has been working on, and also Jason Wang, I think, on an updated satellite spot calibration for GPI. But this has already been applied to this update here in this data set, and it's still this kind of disagreement. Now for Beta Pictoris, they could resolve the disagreement pretty much, but here for these observations, it still remains a little bit disagreement,
Strange. Is there any other question for Jens? I have another one in the meantime.
Sure,
at some point you showed the results of gravity on Beta Pictoris C, and you showed the radius as a function of mass and the predictions for hot start and cold start models, if I remember correctly. I was just wondering, was the photometric radius, this one, what was the radius? Is the radius here the photometric radius? How would you explain this mild disagreement between the Beta Pictoris C points and the predictions? Could it be due to extinction?
No, in this case, we didn't take into account any kind of extinction. So I think the conclusion from Matthias here was that the data point is rather in agreement with core accretion. I mean, the error bars are also relatively large. So I think they didn't interpret that as worrying, and that probably Beta Pictoris C would not agree with the current core accretion models. But it seems like the estimate is a bit low, so it could,
But how was the radius inferred in this one? Is it just from the spectrum, fitting a spectrum and inferring the photometric radius?
I think that's what they did, if I remember correctly.
Okay. Okay, so if there's a little bit of extinction that's not taken into account, this could underestimate the radius.
Yes,
possibly.
exactly.
Yeah.
Exactly.
Okay.
Yeah. And yeah, I mean, the conclusion was that it's probably rather some kind of warm start core accretion and not hot start core accretion.
Okay.
Maybe it depends. I don't know exactly what these models here assumed. Maybe if you would have even like colder core accretion models, then you would get an even better agreement with this measurement. Yeah.
Okay. So there's a question before from Ethan, which was, I mean, basically, if the main point of gravity is to follow up things, why does it matter that you get false positives?
Right. This is a good point. And so what I have been hiding a little bit is that these correlation, where is it? Yeah, this correlation business here that I've been showing. This is basically when you do full-on axis observations with gravity. So in the exoplanet observations where we have dual field with both the science spectrograph and the fringe tracker, we also account for the correlations in a very similar way. But this kind of model that I've been showing here is for a different observing mode. So in that case, you don't have the two spectrographs. You basically just do your science spectrograph observations, and you try to image a circumstellar environment and search for some companion or some disk structures in the circumstellar environment. So that is much more relevant to a different observing mode. Yeah.
Gotcha. Can I ask a follow-up while we're there? So I was curious about this. You were using this discrepancy between Gaia and Hipparchos to look for planets, basically. Is that been done widely? Is that something you can do on like every star, or is it just like very specific case?
Yeah, so this has been pushed forward by Pierre. And I think he has quite a big paper where he looks at those proper motion anomalies for a huge sample of planets. And this can be done for pretty much every system. You can create this kind of plot that shows you, I mean, it's making the assumption that the anomaly is caused by some companion in the system. And then you can make this plot to which kind of companions you would be sensitive given the anomaly and given the specific observations of Gaia. And we have just used his results from the HD206 system to be able to, so he gave us the measurement of the anomaly, and we were then trying to explain the anomaly with this additional companions that we have in the system. But you can do this for pretty much any system, and you can try to predict existence of some planets from that. Yeah.
Interesting.
But of course, most of the systems wouldn't have a very significant or maybe even no proper motion anomaly. Yeah.
I have another question if there's no one else. I found the result obtained with gravity on HD on the astrometry of HD 206893b quite interesting, since you with gravity you suggest there could be a larger eccentricity of about 0.3, right? And possibly misalignments, right? Yes.
Yes.
Yes. Well, if you assume coplanarity, then you get a much lower eccentricity.
Exactly.
But if I'm not mistaken, radial velocity surveys and indirect surveys have found that a significant fraction of giant planets were found on eccentric orbits, right, in mature systems. So not necessarily, so the orbit has not been dampened yet, even in those mature systems, in these older systems than this one. So I find it quite interesting. We also get them at earlier ages. In the protoplanetary disk phase, we can excite those. So I was wondering, maybe it's not implausible to assume that to say it is actually misaligned if we observe them still at older ages in more mature systems.
Yeah, so I think the point that Sebastian Marino was making, that the debris disk and the companion should be aligned due to secular interactions, which it doesn't necessarily mean, I guess, that they have to have zero eccentricity or something like that, but just that there should not be any kind of mutual inclination between the disk and the companion, because the debris should follow the massive companion on a time scale of a few 10 million years. So yeah, I think the argument was not necessarily about the eccentricity of the companion in that case.
Okay.
It's just that it's just the case in here that one of those solutions has a high and one has a low eccentricity.
Okay.
Yeah.
Okay, is there any other question for Jens? Well, I still have another one, a technical question for the non-experts in interferometry. What is exactly the closure phase? You briefly mentioned it at the beginning.
Yeah. Yeah. So closure phase is when you compute the phase or the phase offset over a triplet of telescopes, and the idea behind that is, let me try to go back to where I've been talking about closure phases. Yeah. So if you have some kind of cloud in the atmosphere in only one of the telescopes, then of course you get some phase piston error on that one telescope. And now if you measure the phase on 3 telescopes, they are all affected by different phase piston errors, because the atmosphere is slightly different above those telescopes. But if you compute then the phase difference among a closed triangle of telescopes, then these relative piston errors would all cancel out. And to first order, your closure phases are then independent of these phase piston errors.
I see.
So yeah, that is exactly what you also do with aperture masking and interferometry. You use the same, it's the same idea. You compute these closure phases over 3 of the apertures, and the phase piston errors would cancel out. And it's also the same principle that applies to kernel phase observations, where you also try to find linear combinations of the pupil which cancel out these linear phase piston errors.
Yeah. So this is the quantity you can use for your optical delay lines, right? Since it's not biased, or
well, it's just a quantity that is less affected by these systematic errors from the atmosphere, and a quantity that is sensitive to asymmetric structure in the sources. Yeah. So if you have a perfect point source, the closure phases would always be 0. And if you find some non-zero, significantly non-zero closure phases, then you know there must be something going on in the system. But it's it's nothing than just a better calibrated observable.
Okay.
Yeah.
All right. So if there is no more question, we've used our whole 1 hour slot. So let us all thank Jens again. It was a great talk. Thanks a lot for this.
Yeah. Thank you very much for inviting me. It was very nice to be with you. Thanks for the good questions as well.
No worries. It was a pleasure. So enjoy the rest of your evening in Baltimore. I guess it's already a bit late now.
Yeah, I will go to bed soon.
All right. All right. Have a good
thanks
rest.
a lot for having me. It was very nice. Thanks for the invitation.
It was great to have you.